Hey there, everybody who came back after chapter 4, good job. I know that chapter 4 is crazy. So the good news is chapter 5, much more manageable. Only 3 sections. It is maybe half as long as chapter 4, maybe even not as much. So yay for that. Chapter 5 is dealing with thermochemistry, which I actually think is one of my favorite things in chemistry. I find it really interesting. Thermochemistry is really all about energy and calorimetry and enthalpy. So it's dealing with basically how energy relates to chemical reactions, which can be really cool. It can have so many real world applications. And some of those real world applications could actually be, for example, obviously the energy industry. But some other interesting things are surprisingly food science and nutrition and things like how your mitochondria are working, your energy cells, and then also exothermic versus endothermic reactions. So basically whether or not a reaction is explosive. We all love explosives. It's always fun. All right, so there's a lot of really cool things in energy and thermochemistry. It's very interesting stuff. Okay, so in this, let's talk about a few energy basics. These energy basics are chemical changes, and their accompanying changes are so important in our everyday world. As I was mentioning, metabolism of food, fuels, fossil fuels and other things, consumption of raw materials, all these important things. So what that really brings us to is the science of thermochemistry, which is the study of the heat absorbed or released during chemical and physical changes. And this is super important because heat absorbed is also heat required. The reaction that we're doing will not happen without giving it heat. Released can also mean produced. There are many times, for example, in the burning of fossil fuels, we're not doing this because it's fun to make CO2, or at least we shouldn't. We're doing it because it releases energy, either heat energy or something that would turn into mechanical energy or electrical energy. So it's not just absorbed and released, it's also required. So the energy cost of something, which is very important in so many different things, and the energy produced. That brings us to our first law of thermodynamics, which is also called the law of conservation of energy. During a chemical or physical change, energy can be neither created nor destroyed, although its form can change. Okay, so energy. How are we defining energy? So we're not even going to get into all the different kinds of energy in this class because energy itself is a huge field. We're going to look at a small part of energy. Okay, but energy is defined as the ability to supply heat or do work. And we're going to be looking at pieces of both of those throughout this chapter. There's 2 main types of energy. One is potential energy. And this is defined as the energy an object has because of its relative position, composition, or condition. But most people think of potential energy as stored energy. Okay, so stored energy might be the water that's being held behind a dam that has all this energy just waiting to be released. You might also think of stored energy as the energy in gasoline. When it's sitting in gasoline, it's not doing anything. It's just there waiting to be released. The chemical energy in our food is just waiting to be digested. So stored energy, it's energy that we're going to use later. Kinetic energy is the energy that an object possesses because of its motion. This is energy in motion, moving energy, very important, mechanical energy and all kinds of things like that. Now we have another kind here, thermal energy. Thermal energy is a type of kinetic energy associated with the random motion of atoms and molecules. So why? Well, temperature is a quantitative measure of hot or cold. So for example, if I say, whoa, it's 30 degrees out today. Well, if I say it's 30 degrees out today, is that hot or cold? Okay, because it really depends. Because if that's 30 degrees Celsius, it's really hot. If that's 30 degrees Fahrenheit, it's cold and you need a coat, unless you're my teenage son and then he's wearing shorts. If it's 30 kelvins, you're not even on planet Earth in a natural place. You're like out there somewhere, or you're in a lab that's being super cool. So 30 degrees in and of itself doesn't tell you anything. We remember that from chapter 1. It's this idea, okay? So high thermal energy is something that's hot, okay? And it has fast moving molecules. You have slow moving molecules, you have low thermal energy, and something that's cold. So the colder something gets, the slower the molecules are moving and vibrating. The faster something gets, the faster the molecules and the atoms are moving and vibrating like this. And it just goes back and forth. It's a continuum. It's not any one thing. It's always this compared to this. So is 30 degrees hot? Yeah, I don't know. It's hot compared to 0. And it's cold compared to 1,000. So it's always this continuum. And I just think those spectrums, those continuums are so interesting. All right, so let's think about heat. Okay, heat is also called Q. Okay, and Q, so this, it's hard to see on here, okay, but this little script here is Q. Lowercase q is the transfer of thermal energy between two bodies at different temperatures. So we all know that if you take something cold and something hot, it's going to change. If you take some ice cubes and you put it in a glass, and you pour hot coffee over them, you will end up with coffee that is neither freezing nor hot, right? That's how you make iced coffee. It's one way, okay? Heat flow is actually a redundant term, but we often use it, especially just in our daily life. Heat flow increases the thermal energy of one body and decreases the thermal energy of another. It's like putting room temperature soda over ice cubes because it's a hot day and you don't want to drink room temperature soda. All right, so when two substances are placed in contact, thermal energy will always flow from high temperature substance to low temperature substance. So we never say that the cold is flowing. We always say that the heat is flowing. Heat flows. So if you have a glass of water, okay, and it's warm because you got it out of your lousy tap and it's, 100 degrees outside, maybe not in May, but and then you put some ice cubes in it. Okay, what's going to happen is that these ice cubes are going to melt. And we all know that, right? Well, why are the ice cubes melting? The ice cubes are melting because here, and actually, let me go ahead and I'll make this. There, we've got our cold ice cube and our warm water. And the ice cube is going to melt because the heat is going to flow out of our warm water into our ice cube. And down here, you can see the same thing. Here we have something hot and something cold, and we bring them together, and the energy flows from the hot side into the cold side until they're both the same temperature. Okay, so you'll notice that chapter 5 has a huge amount of terminology, and that terminology is just so important. The first one is exothermic. An exothermic process releases heat. Remember that we said another word for this might be, instead of releases heat, but produces heat, which is really good because it allows us to think about things in terms of heat being a product. So in an exothermic process, heat is your product. It is what you are making. So this might be the combustion reaction that occurs when using an oxyacetylene torch. Okay, yep, that's one thing that works. Basically, an exothermic process could be anything that's burning. Okay, anytime we're burning something. Another interesting thing about an exothermic process are things like melting. No, that's the other way around. Haha. Thinking backwards. Phase changes. Okay, so exothermic process when we release heat, right? So condensation. See, I said it backwards. An endothermic process is one that absorbs heat. So this might be evaporation. Okay. The example they give here is the reaction in a cold pack used to treat muscle strains. that works. Also evaporation. Also a really important thing in an endothermic process, usually cooking. Imagine, for an example, baking. Okay. If you like to bake, you know that if you mix up those cookies or that bread and you just set it on the counter and you don't actually put it in the oven and turn the oven on, you will never bake food. It will rot before it bakes food. So you have to give it heat. It requires heat. And remember that absorbs also means requires heat. Okay, so heat units. There's some important ones. You're all used to the calorie. Calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. The calorie with a capital C, all right, see this capital C, or large calorie, commonly used in quantifying food energy, is a kilocalorie, okay? And remember that a kilocalorie, 1 kilocalorie, 1 kcal, is equal to 1,000 little calories. But the SI unit of heat, and that's what we mostly care about, is the joule. Okay, 1 calorie is equal to 4.184 joules. And we're normally going to use joules or kilojoules. And again, remember from before, 1,000 joules is equal to 1 kilojoule. We'll use kilojoules a lot, so it's important to have that particular conversion. All right, so heat capacity. The heat capacity of a body of matter is the heat it absorbs or releases per 1 degree Celsius. So you can take anything. You could take your house, or you could take the sidewalk, or you could take a tree, or you could take a swimming pool, okay? For any discrete body of matter, a swimming pool or a house or a sidewalk, the heat it takes, the heat energy, remember that's heat energy that it takes to increase the temperature by 1 degree Celsius or 1 Kelvin is its heat capacity. And we would write Q, remember this is actually a Q, divided by delta T. Okay, this is a good time to point out delta means change. And it always means final minus initial. Okay. Heat capacity is an extensive property. It depends on the amount of substance present. Okay, so that makes sense. Okay, it takes, if you've got a tiny little shallow lake, you know that it gets warmer much earlier in the summer than, say, a very big, large, deep lake. And so you can always look at it that way. So heat capacity is extensive. It depends on the amount of substance present. So we have another thing that we use more often, and that's specific heat capacity. It's C or S, and it's really interesting. A lot of textbooks use C for specific heat capacity, and a lot of textbooks use S. So it really depends like which direction you're going. That really just depends on the textbook that you are using. So if you go on into a different one and you see S as specific heat rather than C as specific heat, it's just the difference in the textbook. Okay, this textbook uses specific heat capacity as little c. This amount is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And that makes it an intensive property because it doesn't depend on the amount of substance, because we're specifying it as per 1 gram. So it could be 1 gram of air, it could be 1 gram of water, it could be 1 gram of gold. And it changes based on that. So specific heat is intensive, heat capacity is extensive. This is just a useful list of specific heat values that we can use. They tell you, so basically helium as a gas, okay, and it depends a lot on what your state is. This is one of those chapters where state is hugely important. Okay, takes 5.193 joules per gram degree Celsius. And then it sort of goes down from there. Water, it's that 4.184. That's one that you'll probably memorize a lot. Ethanol, all the way down to, I think the lowest one on this list is gold at 0.129. Now, the lower the specific heat, the easier it is to heat up. So you'll notice gold is a great conductor, right? It heats up really easy. It doesn't take a lot of energy to heat up. So gold is a great conductor. Water, water's a lousy conductor. Okay, I mean, you think, oh yeah, water conducts electricity. Well, yeah, sure, water conducts electricity with ions in it, but it doesn't transfer heat very well. Okay, so those are always some of the things you'll go into. So you'll be looking back at this list. You don't have to have it memorized. If you were taking a test, if you're doing homework or recitation, or even reading comprehension quizzes, for those, I assume that you have slides and that you have your textbook and things like that next to you. However, if you're taking an actual test where time is of the essence, I will give you your specific heat, unless that's what you're solving for. Okay, now let's look at calculating heat. I need to figure out where I am. There we go. Calculating heat. The amount of heat Q entering or leaving a substance can be calculated as C times M times delta T. Okay, so this is your amount of heat Q. So heat is equal to your specific heat. And that's in joules per gram degrees Celsius times your mass. Now, because specific heat is in grams, the mass has to be in grams. Times the change in temperature, and because this is in degrees Celsius or kelvins, it has to be in Celsius or kelvins. Okay, times delta T. Again, delta means change in temperature, T final minus T initial, and this either has to be in degrees Celsius or kelvins, because remember the increment is the same. They just have to agree. Okay, so endothermic is something that's gaining energy. Remember, we've said that in an endothermic process, we require or absorb heat energy. Because we're gaining in that thermal energy, T final is greater than T initial. And so Q is positive. So if we're endothermic, Q has a positive sign. If we're exothermic, a substance is losing thermal heat energy, T final is less than T initial, then the value of our Q is negative. One of the big things you're going to have to do in this chapter is keep track, like a problem might say, a process gains a certain amount of energy. You know, okay, that means my Q is positive. Or a reaction produces a certain amount of heat. Okay, well, it's producing, it's exothermic, which means Q is negative, and you're going to have to put the sign on yourself. So pay attention to that. Okay, so let's take a look at this practice. It says a flask containing 8.0 times 10 to the 2 grams of water is heated, and the temperature of the water increases from 21 degrees Celsius to 85 degrees Celsius. How much heat did the water absorb? Okay, so this is actually a straightforward one. So Q equals our specific heat. Remember from the previous slide, our specific heat of water is 4.184 joules per gram degree Celsius. Okay, times mass, and that's 8.0 times 10 to the 2 grams, which is the same as saying 800 grams. And the only reason they wrote it like this is to show you that there are two significant figures. It's hard to do in 800. And then we have our change in temperature increases from 21 to 85. So we would find delta T as 85 minus 21. Pull out our calculator. I'm going to start with the 85 minus 21 because you'll see I have a really simplistic calculator. All right. 85 minus 21 gives us 64 degrees times 800 times 4.184. And then this looks really big. We have 2, 1, 4, 2, 2, 0.8. Okay, but look, I can only have two significant figures, 1, 2, 1, 2, 1, 2. Okay, I can only have two significant figures. So what does this become? This becomes 2, 1, 0, 0, 0, 0. Okay, and you put your comma in there, and that's 210,000 joules. Well, that's kind of a ridiculous thing to write. We don't want this in joules. So let's think about this. That also means 210 kilojoules, which makes a bit more sense. And look, you can notice here that we are positive, right? This came out positive because our T final is greater than our T initial, which is perfect because we were talking about heat that our water is absorbing. Calorimetry is used to measure the amount of heat transferred to or from a substance. And calorimetry is its own branch of chemistry, very important in a variety of things. A calorimeter is a device used to measure the amount of heat involved in a chemical or physical process. Many processes measured in a calorimeter occur in solution. And what we mean by in solution is dissolved in water. And you all remember from the last chapter that dissolved in water means aqueous, AQ. Okay, so if the reaction is exothermic, the heat produced by the reaction is absorbed by the solution. If the reaction is endothermic, the heat required for the reaction to occur is provided by the solution. All right, well, what does that mean? What that means is that if we're exothermic, then heat flows from the water into the reactants. This increases the potential energy of the products. Now, if we are endothermic, then the heat flows from the reactants out into the water. I just said that backwards again. Oh my goodness. All right. Clear all this. If we are exothermic, my significant apologies. If we are exothermic, our reaction is producing heat. Okay, that means that heat flows from the reactants into the water of our solution. That lowers the potential energy of our products compared to our reactants, and it increases the temperature of our water. If a reaction is endothermic, then the heat flows from the water surrounding our reactants into our reactants so that they'll actually react. That means that the potential energy of the products increases compared to the reactants, and the temperature of the water decreases. Okay, so now that brings us to a couple of really important things. We have systems and we have surroundings. A system is the substance or substances undergoing the chemical or physical change. Surroundings are all other matter, including the components of the measurement apparatus that serve to either provide heat to the system or absorb heat from the system. Okay, so an example of this system and surroundings in this case might be, let's say that we have a Bunsen burner. Okay, and our Bunsen burner is producing a little flame. That's a terrible flame. And say, Professor Trammell, you're an awful artist. And I would say, yes, I know. Is that a better flame? I don't know if that's a better flame. I'm a terrible artist. Okay, so gas is coming into our Bunsen burner. This is a Bunsen burner and we have a flame here. Now the gas coming out, okay, the gas coming out is reacting with the oxygen. So our gas plus O2, that's what's reacting. Okay, so the gas plus O2, this is our system. Okay, now let's say that on top of our Bunsen burner, we have suspended some water that we're heating up. Okay, so the water, the air, the Bunsen burner itself, these are all surroundings. Okay, so that's another way of thinking, okay, well, what do we have for surroundings? So the thing actually changing is the system, and everything around it, those are your surroundings. This is a picture of a coffee cup calorimeter. Coffee cup calorimeters are amazing because they work so well. We've been using the same ones for years and years and years at SMCC. And it's funny, when I had to start teaching at home because of COVID, I would save. I'm not much of a buying coffee out type of person, but sometimes you'll get them in sort of styrofoam things. I wash them out and I save them, and then I use them in chemistry. And I make my children do at home because that's what weird scientist people do. Anyway, coffee cup calorimeters are excellent. Polystyrene is an amazing insulator, so it's really, really useful. You can get surprisingly, extremely accurate results from coffee cup calorimeters. And also what's basically happening is it's insulating it so that you can measure all of your heat change in here without losing any of it to the greater surroundings. All right, so another way to look at calorimetry is to consider a hot piece of metal in cool water. Okay, so you know that, I mean, that's the whole quenching process for metals, right? You heat them up really, really hot and you stick them in water to cool them down very quickly. If the metal is placed in the water within a calorimeter, the heat will transfer from the metal to the water. And we say within the calorimeter because if you're not in a calorimeter, a lot of your heat's going to escape from before you even put it into your water. The temperature of your metal will decrease while the temperature of your water will increase. Again, hopefully obvious there. Eventually, thermal equilibrium will be reached and both objects will have the same final temperature. Okay, so we can write that, and this is going to be very important in the next slide, as Q metal. So the heat from the metal and the heat from the water are the same with different signs. So we can say the heat lost by the metal is equal to the heat gained by the water, or Q metal is equal to opposite Q water. Let's take a look at a problem. A 360 point, notice that little point, gram piece of rebar, that just gives us 3 significant figures. And that's rebar is a steel rod used for reinforcing concrete, is dropped into a 425 milliliters of water at 24 degrees Celsius. Excuse me. The final temperature of the water was measured to be 42.7 degrees Celsius. So we want to say, well, what was the initial temperature of the piece of rebar? Okay, and you can do that. I mean, it's really hard. If you're heating it up, it's hard to tell exactly what the temperature of it is. Well, you can figure it out by math. Okay, so this is the specific heat of steel is 0.466 joules per gram degree Celsius. And the specific heat of water is 4.184 joules per gram degree Celsius. Okay, so then let's go ahead and process this through. So the Q of our rebar is equal to opposite Q of our water. And remember that Q is equal to Cm delta T. Okay, so we'll do our rebar first, and that says that our C, our specific heat there, is 0.466 joules per gram degree Celsius times the mass of our rebar, 360 grams, times our change in temperature. Now, the final temperature of the water is equal to the final temperature of the rebar because they're equilibrating in the same place. Okay, so that means T final is 42.7 for our rebar, and T initial is what we don't know, equals opposite, hey, don't forget this negative, opposite now specific heat of our water, 4.184 joules per gram degree Celsius, times our mass. They give us 425 milliliters of water, but remember water is about 1 gram per milliliter. So we can just put that in at 425 grams of water. And now we have T final minus T initial, and we have both of those. 42.7 minus 24.0. Okay. So this is where you're going to have to really put on your algebra hat and think about it. And what I'm going to do is I'm going to show you right here, T initial, this is T initial of our rebar is the variable that we're looking for in all of this craziness. Okay. All right. So let's go back to that. So first of all, what I'm going to do is I'm going to start by doing this part here. Okay. So we have 0.466 times 360. That gives me 167.76. Okay, and then I have this 42.7 minus T. I'm just gonna cut it down to T now. All right, and then we have negative here, and let's go ahead and find this whole side. 42.7 minus 24 times 425 times 4.184, okay, and it's going to be negative, so we have 33252.34. And I usually don't worry about significant figures at this point. It makes way more sense to just worry about the significant figures at the end. We know from looking at our problem that we're going to need 3, and we can do that later. Okay, now in order to find this, now what we have is we have 42.7 minus T is equal to negative 33,252.34. I have to take this, here it's times, so I'm going to divide it, 167.76, okay. And this gives us, got to keep that negative, negative 198. Okay, we'll 0.2. We'll keep a bunch of sig figs now. It's always good to round at the end. All right, now we have negative T equals negative 198.2 minus 42.7. Okay, and you get minus T equals negative 241. Now here, I'm going to take that away. Okay, degrees Celsius, and this is T initial. Now see, we have negative T and negative 241. So those just cancel out, and we're left with T initial equals 241 degrees Celsius for our V bar. All right, calorimetry principles. So when we use calorimetry to determine the heat involved in a chemical reaction, the same principles we've been discussing apply. So because energy is neither created nor destroyed during a chemical reaction, the heat produced or consumed by the reaction, the system, plus the heat absorbed or lost by the solution must add up to 0, because remember that these are changes. So this is the change in heat of the reaction, and the change in heat of the solution has to balance each other out. Okay, this means that the amount of heat produced or consumed by the reaction equals the amount of heat absorbed or lost by the solution. I like to just think of that as opposite. Q reaction is equal to opposite Q solution. Okay, so let's take a look at what that might mean. Here we have, it says when 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide, both at 22 degrees Celsius, are added to a coffee cup calorimeter, the temperature of the mixture reaches a maximum of 28.9 degrees Celsius. That's the approximate amount of heat produced by the system, by the reaction, sorry. So when we do this, now what we have to do is we have to say, okay, well, notice that we have 1 molar hydrochloric acid and 1 molar sodium hydroxide. That's interesting, but in this case, it's not important. Okay, what is important is it says that we have 50 milliliters of our HCl and 50 milliliters of our NaOH, and they're mixed together. That makes up our total solution. Now, we are aqueous and we are not terribly concentrated. That means that we're going to still be using the density of water. Remember, the density of water is 1 gram per milliliter. So what that means is that I have 100 grams of solution because I have 100 milliliters of solution. So that's going to be important. Okay, we're mixing those together. They're added in a coffee cup calorimeter. Okay, so now the next thing you'll see this, they're both at 22 degrees Celsius when we mix them together. That means that T initial equals 22.0 degrees Celsius. The reaction, as it's reacting, is very exothermic and it pushes a lot of heat into the water. Okay, so that means that our T final, after the temperature has gone up, is at 28.9 degrees Celsius. And they want to know what is the approximate amount of heat produced by this reaction. So we say, okay, well, now we're coming to our Q. Q is equal, again, remember, Cm delta T. Okay, we are dealing with aqueous solutions. So because we're aqueous, we use the specific heat of water, 4.18 joules per gram degree Celsius. Okay, so we have 4.184 times our mass, which is 100 grams, times our change in temperature. 28.9 is our final, minus 22.0 for our initial. Calculator, so we get 4.184 times 100 times 28.9 minus 22. Okay. This leaves us with a Q value equal to positive 2886.96. I can only have 3 significant figures, and this is weird because it's positive. Why is it positive? You might be thinking to yourself, well, let's do 2 things here. First of all, let's find our significant figures. Positive, we can have 3 of them. So this becomes 2890. And it's joules because of our specific heat. Okay, you think, why is it positive? Because we said this was exothermic. We said it produced heat. Well, here's the deal. This is positive because it's Q of the solution. We're not measuring the ions that are coming together to form water. We're not measuring them. We're measuring the temperature of the water surrounding the ions. Okay, remember that here we have our beaker with our water in it, and we have H+ ions and OH- ions coming together, and these come together to form our stuff. So the H+ and OH- are our system and our reaction. Okay, the water around us, remember, because it's aqueous, is our solution or our surroundings, because the water that we're measuring surrounds the reaction. Okay, so the heat absorbed by the solution is 2,890. You could say that the Q of our reaction then is negative 2,890 joules, because the acid and the base coming together are producing that heat. Okay, but either way, you say the heat produced by the reaction is 2,890 joules. That brings us to enthalpy. You can see how these things are just interrelated so well. And again, if this feels really fast, please feel free to pause the video, take a deep breath. If I were in class, I would be waiting for you to write things down, but I don't have to wait for you to write things down, because for you can just pause it and take notes and then come back to me talking. Okay, so thermochemistry is a branch of chemical thermodynamics, the science that deals with the relationships between heat, work, and other forms of energy. Okay, so the total of all possible kinds of energy present in a substance is called the internal energy, U. And this could be a little bit tricky. This textbook uses U. Many textbooks use just a capital E for energy. So U, again, just like C versus S, U versus E, you're going to see one or the other. I will use U because that's what this text uses. But no, if you go on to a different book, it will be different. Okay, so the relationships between the change in internal energy, delta U, remember delta means change, heat, that's Q, and work, W, is summarized in the first law of thermodynamics. It says the change in energy of the system is the heat plus the work. Okay, so let's take a look at that. Energy can be transferred from the surroundings into the system. When that happens, the system absorbs heat from the surroundings and you have a positive Q. Or the surroundings do work on the system, and in that case, you have a positive work. When the surroundings are doing work on the system, if you're talking about pressure volume work, then you are compressing the gas. Now, energy can be transferred out of the system into the surroundings. In that case, the system releases heat to the system and you have a negative Q value. If the system does work on the surroundings, you have a negative work value. The system is doing work on the surroundings and you're talking about pressure volume work for gas, then this is the expansion. So expansion of a gas goes in here as well. Okay. Okay, so let's take a look at internal energy. So remember that when we had internal energy, we had delta U equal to Q plus W. Okay, let's take a look at some expansion work or pressure volume work that I mentioned in the last slide. A system pushes back the surroundings against a restraining pressure, or a surroundings compress the system. When a gas expands, delta V is positive. This V2 minus V1 is delta V. But we need work to be negative in that situation, so delta V and W have opposite signs. Okay, now the interesting thing here is that this must be pressure in atmospheres. So here, this is pressure in atmospheres and volume in liters. That gives you work in liter atmospheres. Okay, so whenever you do this within this, so here, Q is in joules and you find work in liter atmospheres, and that's not okay. So you have to convert your work to joules. And here's the conversion. 1 liter atmosphere equals 101.3 joules. Nope. Okay, so let's take a look at how that would work. We have a balloon and it's being inflated by heating the air inside it. The volume of the balloon changes from 4.00 times 10 to the 6th liters to 4.5 times 10 to the 6th liters by the addition of 1.3 times 10 to the 8th joules of heat. The balloon expands against a constant pressure of 1 atmosphere. Calculate the change in energy. Okay, so now what we need to do is we need to stop and we need to think what some of this stands for. Okay, so here we have a balloon. Now, first of all, we have the addition of 1.3 times 10 to the 8th heat. So that means that Q equals positive 1.30 times 10 to the 8th joules. Now we need to find work, okay, negative P delta V. Okay, so work is equal to negative P, well, our pressure is here at 1 atmosphere. Okay, and then we have delta V, V final minus V initial. So we're going from 4 times 10 to the 6th to 4.5. That means that our V final is 4.50 times 10 to the 6th minus 4.0 times 10 to the 6th. This gives us a work value of, calculator and everything, all right? Nope. This gives us a work value of negative 5.0, our 2 significant figures here, times 10 to the 5th liter atmospheres. Okay, well, again, we said that if heat's in joules, this needs to be converted. So before we can go on, we need to say, okay, well, if I have negative 5.0 times 10 to the 5th liter atmospheres, and 1 liter atmosphere is the same as 101.3 joules, this is how I do this calculation. And that would be over 1, okay? So I get 5.0 times 10 to the 5th times 101.3 joules. And what I get is a work value of negative 5.07 times 10 to the 7th joules. And now I have agreement of units. So I can find the change in energy that we're producing here. So delta U now equals our Q value positive 1.3 times 10 to the 8th joules, plus our work value, negative 5.07 times 10 to the 7th joules. And when I add those together, I will get 7.94 times 10 to the 7th joules. And it is positive. Okay. I can also write that as 7, 9, 4, 1, 2, 3, 4, 5. Okay, 794,000 joules or 794 kilojoules. So these are all appropriate responses if it doesn't specify how I want it. Okay, some of these are long problems. So now we're to enthalpy, and you can see each one of these, again, just so related to what we had before. Internal energy, that delta U, is an example of a state function or a state variable. The value of a state function depends only on the state that a system is in and not on how that state is reached. A good example of that is altitude. Altitude is a state function. It doesn't matter whether you take a ski lift to the top of a mountain or drive to the top of the mountain or hike to the top of the mountain. The amplitude, the height at the top of the mountain is still the height of the mountain, regardless of how much effort you put into getting there. And that's a great example of what a state function is. Energy is also a state function. And we talk about something called enthalpy. Enthalpy is defined as the sum of the system's internal energy and the mathematical product of pressure and volume. So it's H equal to U plus PV. Well, wait a minute, don't you remember U was equal to Q plus W, which means that U was equal to Q minus P delta V. Okay, well, that means that U plus P delta V, these will be deltas now, is equal to Q. Okay, well, that's kind of our little hint there. I think I might even be getting away ahead of us, but that's okay. I'm getting into the next part. That means Q, so equals delta H at constant pressure. So sometimes that doesn't work out quite correctly, but that works for constant pressure. Okay, so what is delta H? Delta H is also a state function, just like delta U. Enthalpy values for specific substance cannot be measured directly, which is why you keep seeing me write delta H, delta U, because we really can't look at them except as a before and after our chemical processes. If delta H is less than 0, we have an exothermic reaction. Okay, so that means that if delta H is negative, we're exothermic. And if delta H is positive, greater than 0, then we're endothermic, just like the sign is for Q. Okay, all right, so that brings us to basically what I was showing on the previous slide, because I always tend to get ahead of myself, is that commonly chemical and physical processes occur at constant pressure. And that's because anytime that you're doing something open to the environment, you're baking cake, you're baking cookies, you're working in a reactor. Anytime that you're open to the environment, you're working at environmental pressure. And you have to have very specific calorimeters called bomb calorimeters to work at constant volume instead of constant pressure. And those are only useful in certain circumstances. A lot of times a simple constant pressure calorimeter is much easier to deal with. Okay, so at constant pressure, which is where we mostly are, delta H is equal to delta U plus P delta V, or it's the same as Q. So everything that we've been talking about so far, Q is equal to this, Q is equal to that, Q is equal to this. Well, now we're going to be using the term delta H. An interesting thing is Q is usually referred to in joules and delta H is usually referred to in kilojoules. One small change there. A thermochemical equation represents changes in both matter and energy. So what you'll see here is you'll see this thermochemical equation, and it's just a simple equation here and an energy part to it here. Okay. Now, what this means is that when 1 mole of H2, hydrogen gas, reacts with half a mole of oxygen gas, it produces 1 mole of liquid water and 286 kilojoules of energy. This negative 286 kilojoules means that it's a product. It means our energy is a product. Now, if we turn this around, what we're saying is that 1 mole of liquid water can be separated into 1 mole of hydrogen gas and half a mole of oxygen gas by adding 286 kilojoules of energy. Okay, so in this case, with this positive here, your energy is a reactant. And when your delta H is negative, it's product. So when it's negative, it means we're releasing it. And when it's positive, it means you have to give it to the reactants in order to get it to work. Okay, so let's take a look at that a little bit. Another important thing here is that it's by reaction. So it's negative 286 goes with 1 hydrogen, half an oxygen, and 1 water. Okay, if we want that to be 2 hydrogens plus 1 oxygen yields 2 waters, because we don't want the halves in there, then we have to multiply our delta H value by 2. Now, if we multiply by a half, and we get half a mole, quarter mole, half a mole, then we get the same thing. Half times negative 286 or negative 143. So the important thing there from the previous slide is that if you flip the equation, you reverse the sign on delta H. If we multiply the equation by a coefficient, then we multiply delta H by the same one. And those are the 2 main tenets to Hess's law, which we'll be doing next. The delta H of a reaction depends on the physical state of the reactants and products. For example, if gaseous water was formed instead of liquid water, you would get not 286, but negative 242. So it's very important to always look at that state. Okay, so let's figure out how to use some of this information. We have a thermochemical equation for the reaction of 1 mole of sucrose. So 1 mole of sucrose plus 8 moles of potassium chlorate yields 12 moles of carbon dioxide. And I do not, this is not showing up, too light. So 1 mole here and 8 here. And 12 yields 12 moles of carbon dioxide, 11 moles of water, and 8 moles of potassium chloride. Okay, and there's a lot of information here. It tells us that we have 2.67 grams of sucrose. And to top it off, it's a limiting reaction problem because it tells us that we have 7.19 grams of potassium chloride. And when you have these 2 limiting reactants, you have a delta H value equal to negative 43.7 kilojoules. Okay, so what it wants to know is write the thermochemical equation for the reaction of 1 mole of sucrose. Well, this is a pretty big molecule, so we know that this isn't 1 mole, and we don't know exactly how to figure this out because we have 2. Well, in this case now, we have our step 1, and step 1 is going to be determine the moles of sucrose and potassium chloride present and the limiting reactant. Okay, so this is another way to figure out limiting reactants. So first of all, we say, okay, well, let's start with the sucrose. Here we have 2.67 grams, and I want to know how many moles I have. So using the C12H22O11, then what we can say, we calculate that up and we find that we have 342.297 grams of our sucrose per mole. That means that we have 0.00780 moles of sucrose. Okay, now let's look at our potassium chlorate. KClO3. Well, here we have 7.19 grams of our potassium chlorate times 1 mole, and our molar mass for potassium chlorate, 1 potassium, 1 chlorine, and 3 oxygens is 122.548 grams. This means that in this limiting reactant problem, we have 0.0587 moles of potassium chloride, KClO3. Okay, well, now how are we going to figure this out? Because we're not trying to find what our product is. And what we want is we want the thermochemical equation to be by 1 mole of sucrose. Well, notice how 1 mole of sucrose goes with 8 moles of potassium chlorate. So we could set up a little thing. We could say that if we have, if we want an 8-to-1 ratio of KClO3 to sucrose, well, what that means is that we could take this 0.0587, and if you divide it by 8, okay, then you get 0.00734 moles of sucrose. So this would be an 8-to-1 ratio of KClO3 to sucrose. I probably won't do this to you on a test. I will probably give you only one thing so that you don't have to figure out the limiting reactants as well, because this is a tricky way to do it. Okay, so we have 0.780 moles, but we're only going to use 0.734 moles of our sucrose because KClO3 is our limiting reactant. We can use all of our KClO3, but only 0.00734 moles of our sucrose. Okay, so that means that the 0.00734 moles of our sucrose is associated with this delta H value. And then what we can do is we can set up this cool little proportion to make things really easy. We can say, well, if we know that negative 43.7 goes with 0.00734, and we want to know what our delta H value is for 1 mole, then you can set up this proportion. Okay, this is kilojoules per mole. Okay, and here we'd get kilojoules per mole. Now, if you remember back to your algebra, the way you solve this, like this, is cross multiplication. And that means that your delta H value is equal to negative 43.7 times 1 divided by 0.00734, or 5953.67, but I can only have 3 significant figures. So this is where I alter it and I say that my delta H value that I'm looking for here is negative 5,950 kilojoules. Okay. And again, in this type of a problem, sometimes I like to show them as really challenging so that you know where this is going. But you probably would not need to do on a test this first step. I would tell you how much you had, and you would be able to figure it out from there. Just this stuff that I have in yellow, blue, and pink. Okay. All right, now we have standard state. Okay, enthalpy changes are typically tabulated for reactions in which both the reactants and the products are at the same conditions. That just makes things a little bit easier for the math. Standard state is a commonly accepted set of conditions used as a reference point for the determination of properties under other different conditions. So the IUPAC standard state is 1 bar, but we're not going to use bars. We're going to use, well, or 1 atmosphere, okay? We're just going to use this 1 atmosphere. It's technically 0.987 atmospheres, but usually we just call it 1 atmosphere because you're just working at sea level. And this is kind of counted in that. These are solutions at 1 molar concentration. And the usual temperature is 298.15 kelvins or 0 degrees Celsius. This ends up being less useful because not all reactions can be carried out at 0 degrees Celsius. The simple delta H0 is used to indicate an enthalpy change for a process occurring at standard state. So this brings us to standard enthalpies of combustion. A standard enthalpy of combustion is the enthalpy change when exactly 1 mole of a substance burns completely under standard state conditions. This is the amount of heat produced when 1 mole of ethanol, okay, here's our ethanol, undergoes complete combustion at standard state. So that means when 1 mole of ethanol reacts with 3 moles of oxygen gas to form 2 moles of carbon dioxide, oh, this should have a gas here, there, and 3 moles of liquid water, okay? Now this is really important. If this was a gas, this delta H value would be different. So it's very important to know that. What happens is we release 1,366.8 kilojoules. Okay, and that's very important because you're not going to burn ethanol for any other reason than producing heat or light. Okay. This is a list of some standard enthalpies of combustion. On the next slide, we're going to be using this bottom one, isooctane. Okay, and you can refer to this if you need it. These are just standard enthalpies of combustion. It's definitely not something that you have to have memorized. Okay, so let's take a look at a problem. The combustion of gasoline is highly exothermic. Let us determine the approximate amount of heat produced by burning 1 liter of gasoline. For this process, we're going to use isooctane as our gasoline, and the density of isooctane is about 0.692 grams per milliliter. So the first thing that I am going to do here is I am going to rewrite the equation from before so that we have that on this page. Okay, and that was 1C8H18 liquid plus 25 halves or 12.5 moles of oxygen gas yields 8 moles of carbon dioxide gas and 9 moles of liquid water. And the delta H that this had at our standard state is equal to negative 5,461 kilojoules. Okay, so now let's come back to our problem that we can do, and let's look at step 1. Step 1 says determine the mass of isooctane in 1 liter, because we're saying that we have 1 liter of our gasoline, but it's not a 1-to-1 ratio like water. Now remember from chapter 1 that density is equal to mass divided by volume. And if our density is in grams per milliliter, okay, well, that means our mass is equal to density times volume. We have to have that agreement. So we're going to find that the mass of our isooctane is equal to our density, 0.692 grams per milliliter, and times, now we can't use liters here because we have milliliters, so times 1,000 milliliters. So the mass of our isooctane is equal to 692 grams. All right, now it says use the equation from the previous slide to determine the heat produced from its combustion. Okay, so now what we can actually do here is this is called thermochemical stoichiometry. You thought you were done with it, but you're not. Thermochemical stoichiometry. So in that case, we have 0.692 grams of our isooctane, C8H18, times, now remember the first thing that you need here is a molar mass. And 1 mole of C8H18 of isooctane is equal to 114.232 grams of our isooctane. Now, you can use this delta H value in place of a molar mass, because what we're saying is that so first of all, it's saying how the amount of heat produced, and we're saying that if you have 1 mole of isooctane, you produce 5,461 kilojoules. So you can say, well, for every mole of isooctane, we have 5,461 kilojoules. And then we pull out our calculator, 0.692 divided by 114.238 equals, and times 5,461. And what we get is 33. Oh, I put in the wrong thing here. Oh, this is one of those amazing times when it is very important to notice. See how it has 692 grams? There. So always check your work, because it's really, really easy. Okay, try that again. 692 times 5,461 equals, divided by 114.238. And now I have, you know what? I don't even have room to do this here. Okay, that equals 33,080 kilojoules per mole. And if you can see here, I can only have 3 significant figures. So this becomes 33,100 kilojoules of heat will be released when 1 mole of gasoline or isooctane is burned. Okay. So now let's take a look at what's called a standard enthalpy of formation, delta HF. It's an enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from its constituent free elements. Okay, well, what that means is that at standard state, remember that's what that little 0 means, 1 mole of carbon and 1 mole of oxygen make 1 mole of carbon dioxide. And the change in energy for that is negative 393.5 kilojoules. Okay, so that's how much energy it releases. And that's very important because it tells us kind of what that delta H is associated with it. Okay, so let's take a look at this. It says, write the heat of formation reactions for ethanol and calcium phosphate. Okay, so well, it says, remember that delta HF reactions are for forming 1 mole. Okay, so we have 2 moles of carbon graphite here, plus 3 moles of hydrogen gas, plus half a mole of oxygen will make C2H5OH. And then for making our calcium phosphate, we have 3 moles of solid calcium, half a mole of solid P4, and 4 moles of oxygen gas will make 1 mole of calcium phosphate. Okay, and then you say, well, now we need to associate a delta H of formation with both of these. I'm not going to actually do that. You can find a comprehensive list of heats of formation in Appendix G. For homework, for recitation, and things like that, I'll probably want you to use this Appendix G. It's in your textbook app. But on a test that is time sensitive, so not your little reading comprehension quizzes, but your actual final test for this chapter, I will give you the heats of formation that are important. The thing to remember is that the heat of formation of an element is always going to be 0. Okay, so what does that mean? So you'll have a delta H of formation here for C2H5OH and for Ca3PO4. but the delta H of formation for an element is always 0. And those won't be in there. And that's basically because we don't have to make oxygen gas, it already exists. And we don't have to make copper metal because it always exists. So in these, if you said, what's the heat of formation for oxygen gas? The answer would be 0. All right, that brings us to Hess's law. Okay, I have one practice problem to show you in here, but later in our practice problems for this chapter that we'll be doing either on our Zoom recitation session on Saturdays or in class when COVID has been kind of handled and we can finally be in class again, we will have Hess's law. Okay, so when we'll do a bunch of them in class, it works so much better if we can see them. Hess's law is the enthalpy change of the total process equaling the sum of the enthalpy changes of various steps. Okay, so this works only because enthalpy is a state function, so we can do it in steps rather than one thing only. Okay, so for Hess's law here, it says, for example, we can think of the reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by a two-step process. Okay, so if carbon to oxygen, carbon plus oxygen equals CO2, and that would be negative 394 kilojoules. Okay, and sometimes that happens directly, but sometimes we have this intermediate step where carbon plus oxygen makes carbon monoxide. And then carbon monoxide plus oxygen gas forms carbon dioxide. And the interesting thing here is that you will see with these that they balance out. So when we add these together, see how the carbon monoxide here and the carbon monoxide here can be canceled. And you end up with carbon plus 1 mole of oxygen yields carbon dioxide, exactly like your single step. And then we can combine them. We have negative 111 kilojoules and negative 283 kilojoules, and that yields negative 394 kilojoules. Okay. So actually, I'm looking at my slides and realizing that I don't have a good Hess's law practice problem to show you right here. And that's kind of a problem. So you're going to, I will be right back. No, actually, you know what? Let's go ahead and finish the slides and I will post a different Hess's law practice problem for you or link to a good example of Hess's law in the slides. All right, and the last one that we have here, and again, I will link to that Hess's law in another form, the standard enthalpy change of the overall reaction can also be equal to the products. So here's what is the standard enthalpy change for the reaction, and you can use the appendix G. Now, again, you've got your appendix G, you can look it up. If we do look it up, though, I can tell you that we have that NO2 is listed as positive 33.2 kilojoules per mole. And liquid water is isolated as negative 285.83 kilojoules per mole. And nitric acid aqueous is listed as negative 206.83 kilojoules per mole. And nitrogen monoxide, NO, is listed as positive 90.25 kilojoules per mole. And what you need to remember in here is that we have to work through this as products minus reactants. Okay, so what's that actually going to look like? Well, here we have our products, and we'll subtract out our reactants. So if I look at my product, see how I have 2 moles of nitric acid? That means I have 2 times negative 206.83 plus, here I have 1 mole of NO. So it's just 1 times 90.25 minus, okay, here I have 3 moles of NO2. So I have 3 times 33.2 kilojoules per mole plus, and then I have 1 mole of my water, so plus 1 times negative, 285.83. Right. Okay, so now as we're working it again, there will be more practice problems coming up, lots and lots of practice problems that we will do together to work our way through this. Just making sure that I have lots of practice problems for you. Okay, and let's go ahead and solve this. So we have 206.83 negative times 2. So we have negative 413.66 plus, there's just one of these, plus 90.25. Okay, now we have this minus sign that we need to distribute through. So 3 times 33.2, that means minus 99.6. See how we have this negative sign here and we have this negative sign here. Negative times negative means positive, so that'll be plus, and there's just one of those, 285.83. And then if we're finding our overall delta H for what we're working on, we have 413.66 as a negative plus 90.25 minus 99.6 plus 285.83. And we get an overall delta H of reaction of negative 137.18. All right. See, I promised that chapter 5's lecture was a bit shorter. Thanks so much for sticking with me, and I can't wait to work on these problems with you.